You build your whole plan is structured around your school requirements, and then you change schools in a completely different requirements.
All right, guys, page 32.
He doesn't say.
Remy got a seat. Liam Jacobs got a seat, guys. So. They know I didn't I stopped what I said. Yeah.
I don't even know who Dumbledore is, or I didn't. I use the names.
So yeah, I think the song.
All right, guys, page 32.
This is what skipping 10 corners does to you.
We're going to actually do the power rule process with area a little bit. I want to switch it up a little bit, so I want to do the new handout probably tomorrow. But I think it's easier to start off with just the properties of definite integrals. So indefinite integrals is when you're just trying to find a formula. We're not plugging any values in. There's no boundaries. Here, if there's a definite integral, that means we're trying to look for specific regions area related value. The reason I keep saying area related is because above the x-axis is going to give you a positive displacement, and below the x-axis will give you a negative displacement. So we just have to keep track of our positive and negative regions. So here, if I look at number 1 here, we're looking at the region between 0 and 12, between the curve and the x-axis. Now, these are all nice geometric shapes, so we can actually do this without calculus, but we're using calculus concepts to basically represent displacement or area. So all these are accumulation of positive y values. So all these will end up being positive values. But here, these are all accumulations of negative y values. And so we're going to get a negative displacement here. All right. So at this stage, I'm just going to find the areas of each of these regions. There's a semicircle, I got a triangle, a rectangle, triangle, and a triangle. You can also combine it and represent it as a trapezoid, but I think we prefer triangles. Is a little bit faster to get those areas. So let's just see if we can fill in the areas of all these regions. Let me shade them in so you can kind of see, make sure that we know we're just referring to the region between the graph and the x-axis. Let me zoom in a bit. Okay. So if I want to find the accumulation of the region between 0 and 12, we can just add up all these numbers, right? And anything above are positive, anything below is negative. Any questions there? Here, we're trying to read backwards from 12 to 0. So if we're reading backwards from 12 to 0, everything that we see is going to be opposite. But rather than doing that, what we prefer sometimes is just to flip the bounds and understand that everything is reversed, or every sign is reversed. So this feels more straightforward. We can always read from left to right here. So we can always, if I want to change the order of the bounds, I can always do that, but I just adjust for the fact that everything is going to be opposite. So we pull a negative out in front, and now we can do it this way. So now we can just do things that we normally would, go from left to right, above is positive, below is negative, and then we understand that at the end, things will have to be changed because of the flipped sign or the flipped order of our bounds. So we know the integral from 0 to 12 is 2 pi plus 1. If I put a negative in front, then it's negative 2 pi plus 1, which is negative 2 pi minus 1. Good so far? All right, so some properties of depth integrals, the bounds tell you where to start and where to end. It kind of gives you that width component of your regions. What do you think is going to happen, though, if I start at A and I end at A? 0, because my width, there is no width. My width is 0. I can't have an area with a width of 0. So if my width is 0, my area is always going to be 0. And reversal of limits, if I want to change the bounds, I can always flip the bounds. Just make sure you pull a negative out, like how we did with the example above. Third property, sometimes we have to understand, I think this, we understand this process that anytime we want to do power rule, we know the coefficient is not going to have any impact. It's just going to hang out in front. Same thing here. If I have a coefficient, I can just push it out in front. It's not going to change. It's not impacted by the calculus process. So visually, sometimes it's easier to just pull it out in front and recognize, okay, I can just put that to the side while I take care of what needs to be adjusted. Adjacent intervals. Let's say I had a graph that looked like this. And we're trying to find the area of this entire region. If they're adjacent to each other, then really we can just think of it as, well, the integral from A to C will give me this region. The integral from C to B will give me this region. And if I total that up, because they're adjacent to each other, this will represent my integral from A to B of f of x dx. So the reason that this is helpful is sometimes we have a large region and it helps to break it down into smaller regions. And if we can handle them independently, then we can just add them up and we know that's going to represent the full region that we're trying to solve for. If I have the sum and difference of functions inside my depth integral, I can basically split them up into individual regions. Sometimes it's easier to break them up separately rather than trying to handle a more like a larger, messier problem. Same thing here, subtraction. I can take the integral of f of x and g of x separately, and then just subtract my results at the end. Sometimes that makes it easier to move forward with the problem. Okay, next up, we have the same region as above. We can carry all this stuff down here. If I want to find the integral from 7 to 6, we prefer to read from left to right. So what adjustment can we make to make it easier to think about this problem? Pull a negative out and just, yeah. So we'll just read the graph from 6 to 7, whatever number it is, make it straightforward, and then just make sure that we keep track of that negative at the end. 6 to 7 is showing me a positive 2, so positive 2 is fine. I just make sure I don't forget about that negative I've already established in front. Okay, number 4, I can do 2 things. I can pull the 3 out. I can flip the bounds. Feels a little bit cleaner if I can write it this way. That way I can just take care of this piece and then multiply -3 at the end. So figure out what your definite integral is from 8 to 12. All right, bottom of the page. The graph is not given to you, but they do give you some information. They tell you that the region from -2 to 1 is going to create an area of 4 or a displacement of 4 above the x-axis. The integral from 1 to 5 is going to create displacement of -8. Integral from -2 to 1 is of g of x dx is equal to 8. So try them and see how far you can get on your own with these. Notice the first 2 are talking about the graph f of x, and the third one is talking about the graph g of x. So they're 2 separate graphs. Okay, I think we're okay here, right? The back page is just, you're just adding regions. Nothing really Yeah, figure with the first page. Let's move on to something else. Sorry, wasn't able to incorporate this into your packet. So let's do the packet. Yeah, the other semi packet that you picked up yesterday. It's supposed to be in this region here. I didn't get a chance to put it inside the packet. If you guys can number your pages here, 1 through 8, so it'll be easier to reference them. And the rest are just keys. So you can.
Is it right?
Yeah, that's right. You can number your pages 1 through 8.
Okay. Set number of 1 to 8.
Yeah, 1 through 8. The rest after page 8 is just pages for the keys that I attached. All right. So this is called the first fundamental theorem of calculus. I abbreviate it sometimes as FFTC. There's also a second fundamental theorem of calculus. They're both important. This one, AP exam loves to just do a lot of variations of this. So when we get to the end of the semester, I think we'll be able to see all the different ways that the first theorem can be involved and applied. So yesterday we did power rule. So power rule allowed us to take the antiderivative. So we're basically able to get from an f prime level up to an f of x level, right? We're able to move our function up the chain to the function above it. That's what this is doing here, where the lowercase f to uppercase f indicates that transition, that transformation from the derivative level up to the function level, okay? Or from the function level to the function above it, right? Or from the second derivative to the one above it, to f prime. That's what that lowercase f and uppercase f means. Okay? So that's the relationship there. So whatever transformation that we need to do to get from lowercase f to uppercase f, right now we only know the power rule, but and trig, right? All those trig rules also takes us from a lower level to a higher level. So once we do that, once we take care of that transformation, then we take that new function that we found and built, and we plug in our upper and lower bound. We do f of b minus f of a. What results is the area related value, or a lot of times it's the area of the region under the initial f of x. So if I want to find the area of this region, I go through the transformation, get it out to the upper, to the function above it, to the antiderivative, and then I do upper bound minus lower bound, and the numeric value that I get in return is the area related value. I keep saying area related because if a region is below the x-axis or portions are below the x-axis, it doesn't quite get you the area. But for our purposes now, we can kind of refer to it as quote unquote area. Okay, so as a review from beginning of the semester, we know a general derivative is a slope finding formula function, right? If I find f prime, I know that f prime is a way for me to arrive at the slope of a curve at different points. But the specific derivative is the actual slope. If I want to find the exact steepness on the curve at 3 or at 4 or at 5, this formula will help me get to that specific number for that specific point. Same idea here. The indefinite integral is an area finding function. So when we do integral of 2x, we do power rule, we get x squared plus c. The x squared plus c is an area finding formula, but then when we involve plugging in the upper and lower bounds, that's going to get us to a number that's associated with a specific region under the curve between two boundaries. If a function is continuous on a closed interval, then the function can be integrated on that interval. So let me show you how we can involve the bounds with power rule. So the first thing you do is you want to make the transformation from your integrand to your antiderivative. So the bounds is the last thing you do. Okay. Sometimes I see students want to plug the bounds in as the first step because maybe that's more natural because we read from left to right. So we assume, oh, the 1 and 4 is going to be involved first. It's actually the last thing that we do. All right, let's just, every term is ready for power rule. So let's just apply power rule. And what does that get us here? 3x squared becomes
X cubed.
We add 1 to the exponent divided by that exponent plus
2x squared.
Okay. I'm doing this step before you guys. I'll clean this up later. Minus 1 becomes minus x. Good question. Okay. Yeah, I want to put that out. The plus c for definite integrals, we don't worry about the plus c because the plus c is going to eventually get washed out. So if we're ever doing with definite integrals, we don't have plus c. Okay. Yes, there's a plus c, but eventually that plus c will get subtracted out and it's going to wipe away. Let's see. Okay, so this ends up being x cubed plus 2x squared minus x. Okay, so we've transformed our lowercase f of x to uppercase f of x. Right, so that's what this piece is doing. Okay. Now to involve the bounds, typically the notation we use is we do a half bracket on the right side, then put a 4 above and 1 below. That's what they tell us. And the formula says f of b minus f of a. So guess what number we're going to plug in first? The 4. Yeah, whatever is up top is the first number you plug in. That's a little bit tedious. I'll do the math for us here. Then you do minus lower bound, plugs in. -92 minus 2, which is 9. So this piece is sitting at the integral from a to b of lowercase f of x dx. And then after we do our antiderivative, we're ready to plug in. This is my uppercase f of b, and then followed by my uppercase f of a. Okay. So I just want to kind of map out what we're doing here. This is what we started with. The lowercase uppercase f is the power rule that we took care of. Now every problem is going to be a little bit different. Some we can just rely on the graph. Some we have to actually do calculus and actually find the antiderivative. But whatever it takes, whatever the antiderivative rule is for this case is power rule, and the upper bound, lower bound is represented by the half bracket. The 4 is my b, my 1 is my a.
That for our purposes, we can consider that The area, you ever find out how to find the exact area?
Yeah. So not in the next unit, but a unit after, we're going to have a very specific formula so we can actually find the exact area and not just this quote unquote area. Okay, so again, for definite integrals, we don't have to worry about the constant of integration plus c. It'll always wash out. So the reason why is because this will produce its own plus c. This will produce its own plus c. And then a plus c and the c from the other one will just subtract out. Whatever this constant is going to subtract out with this constant. So that's why it ends up washing out, because both of them are just going to cancel each other out.
So are they going to be the same seed?
Yes, yeah, same C. Let's talk about this problem here. And I think this goes back to why we are calling this kind of area related, not quite area, because sometimes with definite integrals, you may be able to get a negative number in return. And the reason why I get a negative number is because the region that we accumulated is larger below the x-axis than above the x-axis. Let's just practice this problem here. So how antiderivative first, bounds is the last thing we do. So here we go through power rule, we plug in upper lower bounds, we get -3. And the reason why we get -3 is because it's asking for the region between the graph and the x-axis. This is what y equals 2x looks like. Right? And if we're looking at the region between the x-axis and the curve and the graph, between -2 and 1, you can see that there's a larger triangle below the x-axis than over here. 1/2 base times height, this gives me a 4, which I need to convert to a -4, it's below the x-axis. This is above the x-axis, a +1. We accumulate them together, -4 plus 1 equals -3. Reason we get -3 is because we have regions more of accumulation of more values below the x-axis than above the x-axis. So we can think of this as displacement. Next page. We've talked about these properties already, so there's a duplicate from another set of notes that I had. So let's skip this for now, except I do want to talk about part D here. Well, so just a reminder of all the properties, right? If my bounds are the same, 0. I can flip the bounds and just pull a negative out in front. And I can always take a larger region and split them up into smaller regions, especially if they're adjacent to each other. And then I can handle my smaller problems individually. Let's look at part D here. This can be a little confusing because the 3 looks like a 3 that's just on its own, but it's under the umbrella of the integral. So let's split it up so we can kind of see a little bit more how that 3 is getting impacted. Okay, I'm splitting this up into 2 separate integrals. Are we okay with this step here? Now this one, we can use the properties that's given to us. have the integral from 3 to 6. So this is an easy substitution that we can make. That's just -5 times -1. So no difficulty there. What I really want to focus on is this piece here. This, we don't have a substitution, but we can actually go through calculus and solve this. Okay. So essentially it's asking, what is the area under 3 between 3 and 6? Well, we can use power rule to get to our answer here, even though we could draw this out and draw a rectangle as well. What's the integral of 3? 3x. And then we can plug in between our lower and upper bound. Upper bound first, followed by lower bound. I do want to continue to make the connection with the fact that this is basically area under a graph. This we can do without calculus because it's just really asking for what is the area between the graph and the curve y equals 3, which is the horizontal line, from 3 to 6. So I could draw this out. Here's my graph, y equals 3. I'm just looking at what's between 3 and 6. And that's just going to be a nice rectangle here, right? My width is 3, my height is 3. 3 times 3 is 9. So I could do this without calculus, but it's nice to also know power rule can also handle this problem. Yes.
So just keep in mind that definition was constant, the bounds, and understand that that's your width.
Yes. I mean, once we get to more complicated functions, we can't do this.
Right.
But it's nice to just have that concept that, oh, I'm just really finding the area of some region. For easier problems, we can definitely rely on just geometric shapes to arrive at our answer. All right, example 4. This is a good application of what AP exams like to do. Okay, so let's talk about this one. So they say that the integral from 3 to 8 of f prime of x is equal to 10, f of 8 equal to 6, and find f of 3. So here's a reminder that the first fundamental theorem of calculus can be used as an equation solving tool to find the value of an antiderivative at a specific point. Now, this is the way that I present it to you, right? I present it to you like this, that the integral from a to b of f of x dx is equal to uppercase f of b minus uppercase f of a. But there's a lot of ways that we can adapt this formula, this first theorem. It can also work in this instance, right? Do you agree that if I take the antiderivative of f prime will rise up to the level of f? Right. A lot of variations. F double prime can rise up to f prime. Acceleration can rise up to velocity. Velocity can rise up to position, right? So there's like infinite ways, not infinite ways, but there's like a lot of different ways that first theorem can be represented. Now we have all this information at the f prime and f level. So why don't we adapt it for this particular problem and use f prime and f? So in this case, what's my a and b value?
3 and 8.
3 and 8. So I'm just going to fill in as much as I can. All right, I'm just going to use this formula and see if I can fill in 3 and 8 and see what that looks like. So we know integral from 3 to 8 of f prime must satisfy f of 8 minus f of 3, right? This has to be a true statement, right? So maybe we can make a bunch of substitutions and find what we're looking for. What can I replace this piece with?
10.
10, Okay, so 10. What information do we have?
F of A equals 6.
There we go. And that leaves us with f of 3, and we can find f of 3. Okay, so this is a bit of a taste as to how AP exam loves to use first theorem and have these different variations of asking about application of the first theorem. Okay, example 5 is pretty straightforward, I think. We have areas of these regions here, but if I want to find the definite integral, we got to adjust the signs, right? This stays positive 10, but this will be -2, and this will be a positive 3. Yeah, that's it. Add them up. The 3 regions added together will give me 11. Page 3. This is the second fundamental theorem of calculus, which is also a concept that's AP exam loves to involve. It looks complicated, but it's a nice shortcut, and we want to use it to our advantage. So far, we've done indefinite integrals. We know that without the bounds, we're going to take the antiderivative and end up with a plus c, right? It's some area finding formula. Definite integrals is where we're trying to find the area or area related values between 2x values. This is where we do integral of f of x from a to b, transform it to uppercase f or whatever the antiderivative is, and then plug in our upper and lower bound. So now we have a function that is the integral itself. So if there is a function that is the integral itself, we want to be able to know how to work with a problem that feels a little bit more messy in this form. So instead of going from a constant to a constant, we're going from a constant to a moving value of x. So this is what the second theorem means. So imagine you took a definite integral, or you took the integral of some function. And then you turn around and you found the derivative of that result. What do you think you're going to end up with? Or where are you going to end up? If you take the antiderivative of some function, and then you took the derivative of that again. Okay, that's the big idea, is that you end up in the same place. However, if I take a definite integral and the derivative, along the way, it's going to pick up some pieces that's going to stay with it. But largely, your function is not going to change. So if I take the definite integral from a to p of x, it's going to, that upper bound is going to get lodged into that function, and the derivative is going to end up causing the upper bound to produce itself as well. But notice my f of x doesn't change, right? It's largely going to, because I'm taking it somewhere and bringing it back. So as I do that, it's going to pick up some things along the way, but your function is not going to change much. So it feels abstract. So I want to kind of convince you that this is a nice shortcut. So let's do it the way that that's more straightforward. Okay, let's ignore this shortcut and just do the problem straightforward way. So here's example 1. Ignore the derivative. Let's just do the definite integral from 1 to x squared of 2t minus 3. And then after that is done, we'll turn around and do the derivative of that. Okay. So Let's just worry about this piece here, just what's inside. Okay, so power rule 2t minus 3 becomes minus 3t, which becomes t squared minus 3t. Okay, and then plug in what? Upper and lower bound, right? So x squared and 1. Okay, what gets plugged in first?
Squared.
Mm-hmm.
So x to the fourth.
Minus what? After you plug in the x squared, what do we need to plug in next?
1.
The 1, okay. So x to the fourth minus 3x squared plus 2, right? Plus 2. So we're going to turn around and take the derivative of this. Okay. X to the fourth becomes minus 6x and then 0. Okay. So this is the result. Now, look how your variable changed, right? Your t became x because the upper bound did its job of plugging in. But then what did the 1 produce? Produce the constant. What's going to happen with that constant?
Go away.
Go away. So the second theorem is taking that into account. If my lower bound is a constant, this whole process, I can just ignore that constant. That lower bound is going to just get wiped out. It's going to get turned into a constant. It's going to get wiped out. So let's apply the second theorem, and we should get the same answer. So here's second theorem. Let me write it again so we can compare it, the process here.
Can you explain one more time how the constant where they
Yeah, let me finish writing this. So you see how if I plug in my that lower bound into the function, I get 1 minus 3, which becomes positive 2. So then what happens to that positive 2 once I take the derivative of that? Goes 0. So we know that we can basically ignore that lower bound. This lower bound at the end of the process will just go to 0 because that 1, whatever number will get plugged in and create a constant, and that constant is going to get pushed to 0 by the derivative. So we're going to apply the second theorem for this problem that we just did the long way and see if we get the same answer. So the rule says f of p of x. That just means plug the upper bound into the function. No derivative, just go ahead and plug in. So what is that going to get us? 2x. 2x squared minus what? 3. 3, yeah. So we need to write the entire expression, just replace the x squared in for the t. Okay, so that times
2x.
Upper bound's derivative, 2x. Okay, clean that up. 4x cubed minus 6x. So the advantage of this property is we can save a lot of time. We don't have to do a whole calculus process. Oh, find the antiderivative, upper bound and lower bound, and then turn around and find the derivative again. Okay. Especially if problems are unable to be done with calculus. Sometimes we're going to get these second theorem problems where we don't have the skill or we don't have the knowledge to be able to find the antiderivative, but it's asking for the derivative of the antiderivative. So we can essentially cancel their processes out and just follow the step here. Upper bound into the function times the upper bound's derivative. I just want to do it both ways so you can be convinced that this act as a shortcut to doing two processes, especially if we're going somewhere but coming right back. But as we go along that journey, it's going to pick up some pieces along the way. The upper bound is going to get inserted into the function, and the derivative is going to have an impact on the upper bound. Okay, any questions? Okay, that's all. That's all I have for today. I want to revise your homework because it's a little messy with what I've given you. So no homework again tonight. After Friday, I'll send you a list of what the condensed version of the homework is. That'll be due after break. Okay, but I just want to be able to get through as much as I can by tomorrow, and then I'll figure out what I want to give you for homework. All right, come get your phones.
Did you say we didn't have homework?
Yeah, no homework tonight.
I was gonna ask you, the solid point, remember you said we didn't have to do like 30.
Yeah, you don't do that.
Yeah, I was gonna say, if you have to take those, then they didn't want to go through them just to like.
Yeah, send me a reminder.
Okay.
What?
31.
Yeah, think about it.
Think about retaking what?
What?
Maybe there you go.
Yeah. What? Are you doing early? Yeah.
I'll pull
I
up.
think I'm just gonna say that for the action if I read it. It's like
I'm gonna pull up. You're out of the way.
Dude, do you see what is happening?
So if I got like a really bad score on the quiz,
Yeah.
is there any way
Yeah, you
that?
can retake it.
Oh, that.
Thank you.
Don't worry, I'm fine.
What you said?
And I haven't given it back to you yet. Okay, I'll give it back to
That's it,
you.
bro.
Might even find
I know I'll take you like a cool little. Starting.
It's my Christmas gift. It's gonna do all this stuff.
Yo, I'm about to take you further. You doing it on your own or you? Already done.
I'll print it out and I'll bring it to you.
I have a lot of days I missed. I had the AP stuff too. I did the one from last night because I remember it from last week.
Okay, good.
That's good.
This semester is nice. It's all revealed.
Not too much.
Not too much to do. It is pretty. Thank you.
Me and Anika have to keep on later.
Okay. All right. Sounds good.
Okay, bye.
Thank you. All right.
I don't think it matters.
Oh, wait, are you?
Yeah, I mean, you should.
Yeah.